So hello peoples of the internet. So today we'll see the temperature rise at the surface of the airfoil. So over here we have taken an airfoil, okay, and the flow is depicted around the airfoil. So these are actually the streamlines, okay, and this point O is the stagnation point. So what is the stagnation point? So over here you can see that the flow of air is actually coming to a rest at this point O, right? So that means after this point O there is actually no flow anymore. So that means this point is actually the stagnation point. So the stagnation point is a point where the flow actually comes to a rest in a reversible adiabatic manner. So the flow is a reversible adiabatic manner at the point O. So this is the stagnation point. So mainly the stagnation point is the point where the flow is actually coming to a rest, but the conditions are the flow should come to a rest in a reversible and an adiabatic manner, okay. So first of all let us consider the free stream. So let us consider the free stream from this cross section. So we are naming this cross section as 1, and we have already discussed that this point O is actually the point of stagnation or the stagnation point. So we know that at point 1, suppose the enthalpy of the air be H1 and the velocity of the air be V infinity, because we are taking this point 1 at a very large distance away from the airfoil, and at point 2 and at point O, basically suppose the enthalpy be H naught and the velocity will be 0, okay. Why the velocity will be 0? Because at stagnation point are basically the flow is actually at rest, right? The flow is at rest. So if the flow is at rest, so that means our velocity would be 0, right? So that means at point O our enthalpy is H naught and our velocity is 0, okay. And we know, first of all, okay, another thing that we need to mention over here, that first of all over here we'll apply the energy equation. Now over here the flow over the airfoil is actually happening in a continuous manner, right? That means the flow is actually happening continuously, the streamlines are being formed continuously, right? So that means this is an open system where mass is entering the system, the mass is entering the control volume. That means mass transfer is taking place, and as well as heat transfer is also taking place. So that means this is an open system and we are applying the energy equation on the open system control volume. So now you may say that where is the control volume? That I have not depicted over here, but the control volume you can take something like this. You can take the control volume as this. So these are the boundary of the control volume. So now you might say that across the boundary, see that there is a transfer of mass, right? Air is actually flowing through, right? Air is actually entering over here, right? So that means across this control volume there is a transfer of mass. Also there will be heat transfer, right? There will be heat transfer across this boundary. So that means both heat and mass transfer is occurring across this boundary. So obviously it will be an open system. And we know that the steady state open system equation is, it's H1, that is enthalpy at point 1. Now this H1 is actually specific enthalpy, that is enthalpy per unit mass, right? Plus V1 square by 2 plus Q dot. So this is equal to your H2 plus V2 square by 2 plus W dot. Okay, now what is Q dot and W dot? It may come to your mind. So Q dot is actually nothing but the heat transfer that is occurring within the control volume, and W dot is the work, and W dot is nothing but the work transfer which is occurring within the control volume. But for the sake of simplicity, we'll take that neither this heat transfer is being taking place or work transfer is being taking place, okay. So that means what we do, we actually make these terms to be 0. So from here So at point 1, our enthalpy is H1 plus V1 square by 2. So this will be equal to the enthalpy at point 2 plus V2 square by 2. So what is the point 2? Point 2 over here can be taken as point O, right? So what is enthalpy at point O? H naught plus what is velocity at point O? 0. 0 square by 2. Okay, and at point 1, that is our cross section 1, our velocity was V infinite, right? So instead of V1, I'm over here substituting V infinite. So over here we got this equation. So from here I can write H1 plus V infinite square divided by 2 is equal to H naught. Now H1, which is the specific enthalpy at point 1, so this can be written as Cp into T1. So what is Cp? Cp is the, so what is T1? T1 is the temperature at the point 1. Okay, so over here similarly H naught can be written as Cp times T naught, right? So where T naught is the temperature at point 2. Okay, where T naught is the temperature at the surface of the airfoil, that is at point O, right? So over here put this into our equation, we'll get that Cp T1 plus V infinite square by 2. So this will be equal to your Cp T naught. Okay, so from here actually comes our T naught is equal to T1 plus V infinite square divided by 2 Cp. Okay, so as our point 1 is actually the free stream point, right? So that means for free stream we can take T1 as T infinite, right? Don't get confused, it's very easy. It's T1 is actually, it's T infinite, that is the free stream temperature. So plus V infinite square divided by 2 Cp. Now we know that the speed of sound at the cross section 1, so that is at the infinite, so that means at the free stream cross section, we are taking the speed of sound over here at this cross section, that is the infinite cross section. So will be what? Nothing but A infinity. So this will be equal to, what is the speed of sound? Gamma t, right? And at the free stream point, the t is T infinity, so gamma r T infinity. Okay, so just square it, so in A infinity square it will be gamma r T infinity, and we know that gamma r is nothing but A infinity square divided by T infinity, right? From this equation, A infinity square divided by T infinity is gamma r. Now substitute that, so from here we get that Cp will be equal to your what? It will be equal to your 1 by gamma minus 1 A infinite square divided by T infinite. Okay, so this is a relation that you can remember. So now what we will do is that, and let this be equation 2. Now what we will do that we'll substitute Cp from this first equation into this second equation. So on substituting that we'll get, so T naught, so this will be equal to your so this, yeah, so over here this is T infinite plus, so V infinite square by 2, and then there is a Cp in the denominator. We'll just substitute that, so over here this will be 1 over gamma minus 1 A infinity square divided by your T infinite, right? So over here this will be equal to your my bad, so this will be equal to your T naught, so this will be equal to your T infinite plus twice of gamma minus 1 by 2 V infinite square divided by A infinite square times T infinite. Now there is a concept that you need to know, is that Mach number. I'm sure every one of you knows this. So Mach number is something as, it actually is a number that actually determines that whether you are actually moving faster than the speed of sound or slower than the speed of sound. So it is actually velocity divided by the speed of sound. So if it is less than 1, you are actually, you are subsonic. It is greater than 1, you will be so if it is actually greater than 0.8, it's actually subsonic. 0.8 to 1.2, you are transonic, and above 1.2, you are supersonic. Okay, so basically Mach number is, it's the ratio of velocity which we are moving to the velocity of sound at that point, right? So over here at point 1, at this point 1, you are moving with the speed of v infinite, and the speed of sound at this point is, what will be this? It will be a infinite. So that means at point 1, the Mach number will be v infinite over a infinite. So that means m infinite, that is the Mach number at the free stream, will be equal to your v infinite over a infinite. Now over here, see over here, this is v infinite divided by infinite whole square. So that means this term will be m infinity square, right? So that means T naught will be equal to your T infinite plus gamma minus 1 by 2, and this will be equal to your m infinity square T infinity. So overall, if you combine this, you will see that T naught will be equal to your T infinite 1 plus gamma minus 1 by 2 m infinite square. So that means we have successfully found that the rise in temperature will be this much. Why? Because when the air was at the free stream point, the temperature of air was T infinite. But when the air came to a rest in adiabatic reversible manner onto the surface of the airfoil, right, at point O. The point O was this point, right? When it came to a rest at the surface of the airfoil, we see that the total temperature T naught, or the stagnation temperature T naught, will be this term, right? So that means the net rise in temperature when the flow actually came to a rest in a adiabatic reversible manner is this term, right? So that means this was the rise in the temperature. And I'll be coming up with more tutorials in the form of gas dynamics and aerodynamics as well. So you can subscribe this channel. Thank you.